So I'm very happy today that we have Professor Ozgur Yilmaz from the math department at the University of British Columbia. Ozgur is also currently the interim director of the Pacific Institute for Mathematical Sciences. He will, I think this summer, become the actual director of the Pacific Institute for Mathematical Sciences. Ozgur got his PhD from Princeton. He was then an Avron Douglas lecturer at the University of Maryland, and he joined UBC in 2004, I believe. Over his career, he's been the deputy director of BERS, the Banff Research Station, and his research focuses on applied and computational harmonic analysis, information theory, mathematical signal processing. He's worked on problems in analog to digital conversion, source separation, sparsity, compressed sensing, and various applications, for example, in seismic signal processing. So without further ado, the floor is yours.
Thank you, Ryan. And I apologize for this delay. A method that I've used so many times while teaching, while giving talks and so on, collapsed today. So we had to find a different way. So apologies for that. And thank you, Ryan, for the wonderful introduction. It's a pleasure to be here and to talk in the seminar. Now, I'm gonna talk today about inverting generative models, and this is something recent that we did. It's joint work with. I hope the method doesn't collapse any further. Yeah, okay, good. I can write. So this is joint work with Babru Joshi, Xiaowei Li, and Yaniv Plan, all at UBC. Babru is a postdoc, Xiaowei is a graduate student who is about to finish, and Yaniv is, you guys, most of you probably know Yaniv already, is my colleague at UBC. Okay, so the problem that we are looking at, the problem is the big problem is solving an inverse problem. The inverse problems we're going to look at are of the form where you have some observations that are contaminated by noise by a forward operator. Here, X star, I'm going to refer to as signal, mainly because that's what I'm used to saying, calling these data sources. This is the forward operator, and this is additive noise. And the problem that we want to solve is basically, we want to estimate or recover X star, the signal, from the observations Y. And the difficulty we have is this is possibly ill-posed. We don't have enough information to uniquely identify X star from these measurements under this model. So we need to do something about that. And we also need to make sure that whatever we do about that is tractable. So the typical ingredient you need is a signal model. So we need to model the signal class. And we use that model to restrict our search space and to hopefully find a solution that is meaningful. I'm gonna mention a few examples here that I will touch on this talk, which is denoising, compressed sensing, and quantization. Very little, but still. And of course, there are many other very extremely important inverse problems that I'm not going to think about today, but some of our results are applicable to, such as inpainting or general imaging problems and so on. Okay, let me get to how do we model signals. So there are mainly two different approaches, I can say. The first one I'm going to call the deterministic approach, or the function space approach, you might call, where you think of the signals of interest as as a set, as a subspace, or as some structured set. Okay, so this is saying that X star is in some set, which is a fixed subset of a high dimensional ambient space. Okay, and when you do this, the generic program to solve the inverse problem is to look at the minimizer of the basically misfit or loss or whatever you want to call, and this square is redundant here. I'm gonna say argmin of this, where X is restricted to the signal class. Okay, so this is well explored in the literature for tens of years, and you can look at different problems where the signals of interest could be, for example, the set of band-limited functions as a subset of L2. This is very important in analog to digital conversion. In general sampling theory, you could look at sparse signals, let's say k-sparse signals in Rn, or you could look at also learned models. Until you learn the model, your setting might be stochastic, but once you learn the model, you learn the dictionary, and you say, oh, this dictionary is good for this signal class, I fix it, then it still fits into this framework. Let's say learned models. And let me also mention a few forward maps that, again, are associated with what I wrote up there as examples. For example, if you are looking at denoising, your forward map could be identity. Or if you're looking at the typical compressed sensing, classical compressed sensing problem, this could be a matrix, m by n, where m could be much less than n being the dimension of the ambient space. And if you're looking at quantization in various settings, you just look at the composition of a quantizer map with whatever map you have here, something like that. And here Q is a quantizer, which means that it is a map that takes numbers in the continuum and maps it to an element of a finite set. Okay, so this is a very, very quick review of this deterministic approach that I mentioned. Let me do a quick review also of the Bayesian framework. That's the alternative. And this is something we will kind of use to motivate how to use the generative networks to solve inverse problems. Okay, so what's the Bayesian framework? You still have the same acquisition model, okay? The data is collected the same way via forward map with some additive noise. And here X star is your signal, but instead of thinking X star as a map element in a fixed set, now we think of X star as a realization of a random vector. So X star here now is a realization of a random vector. Let's call it X. Okay, so this is random vector. And the distribution Px captures our info. This is where we feed in the prior information we have about the signal. So this is how we restrict our search space, so to say, information about X star. Okay, and when we look at it like this, what we see is now our measurements is also represented by a random vector like this, and we would like to know the distribution of X given Y. So we are given the measurements and we want to find a good estimate. So this is what is called the posterior distribution is the object of interest here. And it gives us what is called the map estimator, which is given by this optimization problem. Okay, so basic stuff. And when we use Bayes' rule to rewrite this in a slightly different way, also take logarithms and so on, we get this minimization problem where we have the log likelihood here minus the log of the prior. Okay, and when we write it like this, it kind of becomes nice because this term depends essentially on noise. And if, for example, we knew that noise was Gaussian, we would get something like depends on noise, and we would get something like this, minus y to norm squared. Okay, and this guy is the regularizer R of x, which is the negative log prior. It depends on the prior distribution. So R of x is on the prior distribution on Px. Okay, so to write down this, to be able to find the solution, we need to have information about the prior distribution. Okay, good. Need the prior distribution. And remember, this is the information we have about our signal class. And we have lots of samples from this signal class. So we can do some statistics, try to understand what kind of distribution we have and try to impose that. And that is a very difficult task. There are ways of doing it, and what I'll show is one way in a moment. But one other kind of shortcut is tie this back to the deterministic approach in some way. It is saying that, you know what if I knew that my signals satisfy something? For example, make the assumption that given, let's say, a basis, orthonormal basis, maybe a wavelet basis or something, the coefficients are distributed according to some law. Maybe they're IID Laplacian. Okay, if I knew this, then this would give me R of x to be some lambda times the one norm of the signal, and it leads to unconstrained assumption. So this is one way of handling this. What I want instead to do, what is more, in some way, what is more interesting, at least in certain situations, to do, and obviously I'm not the first person to do this. This is a very well established method. Use a learned prior. So you go and you try to learn the prior, and maybe with a little bit more accuracy and more specific to the class of signals you have. And what I'm going to look at in the rest of the talk is learn this prior in the form of a deep generative model. Okay, so there is literature, exciting literature about generative models, about how to train generative networks. And two very common ways are the variational autoencoders and the generative adversarial networks. I will assume that somebody knows how to do this, and they give me the model that is trained. Okay, so this is not about how to train this model to learn the prior. This is, whatever I say from this point on, assumes that somebody who knows what they're doing has trained the network and created a model that works. So we work with a generative model, and we want to incorporate that into the solution of various inverse problems that I've mentioned before. All right, so let me here review or mention at least some related literature which inspired this work. So this is by no means meant to be a comprehensive literature review here, but I want to say that the paper by Bora, Jalal, Price, and Dimakis on compressed sensing with generative models. This is a 2017 paper, introduced this idea of using generative models in problems like compressed sensing. And then the work, several papers by Paul Hand and his collaborators approached the same problem with an algorithmic angle, and they basically proved that an algorithm based on gradient descent updates does converge to the solution in a particular way if certain conditions are satisfied. I'll try to summarize that in a minute. And this is the work we will generalize, or we will take and change a bit and show that we can still do things and maybe a little bit more. Okay, so let me just try to now define the setting and terms a bit here. So we're going to have a generator network. A generator network is a map from Rk to Rn. Here, this is an expansive network, K is less than N, and G maps a vector in a Z, which is coming from a known distribution, and then typically it's normal IID Gaussian entries in Rk in the small dimension, and it maps it to a random variable X or random vector X in the big dimension. All right, so this is called the latent code, and this is the signal. So the signal is in the big dimensional signal space, and it is basically encoded to a smaller dimensional vector, which is reasonably called a code. This is the latent code. And the distribution of Z is known. It comes from the IID Gaussian distribution. The distribution of X, G learns, G is, a network is trained so that G actually takes this Z and maps it to the signal space in the way that the distribution of G of Z matches the distribution, the prior distribution of the signal. Okay, so Px is the prior. And therefore, we can sample the prior space. And this is why we can generate images like faces that look like nobody. Okay, we have the space that corresponds to all faces, and a generator network learns the distribution, the prior distribution, and then to sample from that prior distribution, we just need to pick a random Gaussian vector and then apply G on it. Okay, so this is my prior. Now I want to go back to the inverse problems setting. I remember I have the regularizer, which is the negative log Px. And what I'm going to do is now I'm going to relax this quite a bit and tie back to the deterministic setting. So I'm going to think instead of a different regularizer, which is basically infinity if x is not in the range of G, and 0 if x is in the range of G. Okay, so this is a very coarse approximation. And if you do this, you're saying that my search space is now limited to the range of the network G. Okay, so, and with that, you get to this solver or algorithm or whatever you call it, arg min. I want to minimize the error, and I want to minimize the error staying in the range of G. I call it R of G now. Okay, so this is the problem, and you can turn this also to something that is a little bit easier to think about, which is I'm going to minimize over all Z in RK, A of G of Z minus Y to norm, and then X, of course, I want X tilde, which is going to be G of Z. Okay, so this is the optimization problem that we get by making this approximation.
Ozgur, we have a quick question in the Q&A about how the choice of K is usually made, the dimension of the latent code.
That is a very good question, and it's about the assumed dimensionality of the signal. And I know that, and I have to answer this with a disclaimer that I'm not an expert in training these networks. And it's a choice that is done when you train these networks. But I know that if you choose it too low, then you get, your generator it gives a very caricature-like picture of faces, for example, if the signal class was faces. And if you pick it too high, it becomes more surreal. So the expressivity of the network needs to kind of match your space. And I think there's a lot of trial and error about finding the right code.
Great.
I hope that, yeah. Okay, so let me say a little bit about how this is related to the generative neural network. So that will also give me the opportunity to restrict my attention when I prove things. So our generative neural network is going to be something like this, and forgive my bad drawing here, and it's gonna go, and it's gonna expand, not necessarily strictly, by the way, I make that remark, which is kind of cool. And this is W1, W2, and so on. I get WD here. Z goes in, X comes out, and the width of these layers are N0, N1 through ND. And each of them also have an activation function sigma, which is the nonlinearity. Okay, so I'm gonna say this is a fully connected network. For now, let's also look at the situation where I don't have bias. Okay, I will say something about that. In fact, I will relax that at the end of the talk. But for this part, let me just say this is sigma of WD, sigma goes like that, and sigma of W1Z, where these WI are weight matrices. So WI is NR NI minus NI minus NI times NI minus 1, and sigma, I'm gonna restrict myself to ReLU for now. And that means, as we all know, I'm just writing otherwise. Okay. This is my restriction. I'm gonna restrict them further, but that's just get to this, and also I'm gonna assume I'm looking at the compressed sensing scenario. Okay, so my goal for a little bit now is solve this problem. Let's call this here star. Okay, so I want to solve star with this G. Okay, and with, let's also write that with A is the map, the matrix, the compressive sensing matrix, if you wish, M by ND, and M is much less than ND. Okay, so I want to solve this optimization problem in this setting. And this is again my compressed sensing matrix. All right. Now, I think we have everything we need to state the algorithm. Basically, I'm going to leave the which one should stay. I think I will leave the. It doesn't matter. So let's just go algorithm by, this is Paul Hand, and then actually let me write it in order. Wang, Hand, Echo, Voroninski. And what they do is they look at this iterative method where you get zk is equal to zk minus 1 times some step size. And I'm going to write this and then explain what these are. D1, W1 transpose, D, WD transpose, and then we have phi transpose, and then that is multiplied by phi of G of zk minus the measurements. Okay. So this is an iterative algorithm. As I said, or maybe I didn't. It's based on gradient descent. So these rows. These are matrices which select active rows of G, I'm going to call, at each layer, because remember G has the ReLU function. So some of the rows of each of these matrices Wj, maybe I should just say Wj here, because so when you take Wj and multiply it with whatever vector you're multiplying it with, it's going to be like some of the rows of it will result in negative inner products, and so they will be basically replaced with 0 when you have sigma in front of it. So when you do that, that corresponds to discarding that row of Wj. And this D1 through DD are doing exactly that. They are diagonal matrices with 1 or 0 on the diagonal, and the choice of which ones are 0 depends on which ones are basically giving negative inner products with your matrix, and that makes it dependent on its input. So this is just a way of writing. In fact, all these matrices are dependent on the iteration, and specifically they're dependent on the specific input to the ReLU function at that layer. Okay, but it's a way of writing it, and when you do it, they prove that and they make some assumptions, of course. If Wj are appropriately normalized IID Gaussian matrices, okay, so we have Gaussian weights. If phi is appropriate for compressed sensing, okay, so there has to be some kind of RIP condition on the associated subspaces, which is related to the range of G. But Gaussian matrices, for example, satisfy that. And if M is sufficiently large, again, you need to have sufficiently many samples, you get ZK converges to Z star, and G of ZK goes to G of Z star. And this holds with high probability. Okay, so this is the result that motivated us to look at this. There are a bunch of assumptions that one needs to make. But when you do that, it gives you a provably convergent algorithm. For architectures, fully connected architecture, but you can pick your at least the width of each layer and so on. Of course, there are constraints. I should probably also write that, provided it is a strictly expansive network. Okay, and there's a ratio of expansion that need a minimum ratio of expansion and so on. Okay, so what do we do to deal with some of these limitations, and also to make to come up with a maybe simpler to implement algorithm? And that brings us to our contribution. It's an algorithm called plugin, partially linearized updates for generative inversion, I believe, is the one that we settled. And the main idea is really an observation that led to everything that will follow, which is, why don't we drop DJ? Okay, so what happens now? And then I'll explain the motivation behind this. But let me just write down the algorithm without DJ. Okay, so then we get this ZK plus 1 is ZK minus 2 to the D. I'm fixing the step size. I can deal with different step sizes, but this is the right one, at least for the proof. Transform A transpose to WD transpose, and then I have phi transpose, and then I have phi of ZK minus Y. Okay? So this is plugin. All right, so let me first state the assumptions that I have to make and what we can prove. Okay? And then I'll discuss a little bit what motivated us to do this, and some sketch of the proof. And then I'll talk a little bit about the extensions. I know I have limited time. I started a bit late, but I tried to make sure that I cover the relevant aspects as much as possible. Okay, so the assumptions I have. The first assumption is sigma is ReLU. The second assumption is, and I will soften this in my remarks later. So this is the set of assumptions we had to make in our paper in NeurIPS just this last December. I will relax them based on recent work that came after that, but let me just give it the way it is in the paper first. So the WI have to be these, again, they were NI by NI minus 1, and we want them to be IID normal 0, 1 over NI. Okay, appropriately normalized. The next assumption is we have an expansivity requirement, just like the work by Huang et al., but it's slightly different. The lower bound on Ni is in terms of the exponential part. This is not the different part, but in terms of not Ni minus 1, but N 0. And there's some logarithmic terms here which are not consequential. So this is important, and it will allow us to actually consider networks that are not strictly expansive. And to our knowledge, this might be the first work that can do that. The next is I have phi is the compressed sensing matrix is M by ND, and this is IID again Gaussian. And here M must be bigger than some constant that depends on the depth of the network, and 0 and some logarithmic terms again. Okay. And the next assumption is about noise. Noise does not depend on the random matrices that we have. So you can start with some deterministic noise or whatever. It's just that it shouldn't be dependent on these matrices. And there's no upper bound on the noise level, which is different from other works in the literature. So we can handle any size noise. Eventually, everything will be fine. Fine meaning, of course, we go down to the noise level. It's okay. Under these assumptions, and this is as I said, based on our work, recent work that is published. We are assuming that, let's give this distance a name, Z0 minus Z star. Let's say this is less than R. I have no limitation on R, by the way. It is just a parameter I need to know, because whatever comes up from this point on depends on this distance. But I don't have this, not a local result. So that the step size is 2D, 2 to the power D. Then what we get is Zk minus Z star is 2 to the minus K times R. This is why R, it's not important what R is really, times the noise level, plus the noise level. And the error in the signal space is 3 times this. 3 times this, 2 to the minus K, a bound on it, because we make sure that with high probability G is Lipschitz with Lipschitz constant less than 3. Sorry, C times 8. Okay, and this is with probability bigger than 1 minus 2K plus 4 e to the negative 10 and 9. Okay, so this is the main theorem that I want to state. And now let me say a few words about the implications. So some remarks. The first one is assumption A2, which is this one here, is, as I mentioned, A2 allows contractive layers. Not the first layer, but after that, because the lower bound is in terms of N naught. Okay, so if you expand enough in the first layer, then you could have nothing expanding after that, or whatever. And this is an advantage, and then it's apparently it is often the case in practical networks that there are some contractive cumulative layers towards the end. And it's also something that is not dealt with before, as far as I know. Again, I might be wrong, but I believe this is the first work to do that. The second one is convergence is geometric from the beginning. Not in the Huang et al. Algorithm, they have to wait for finite time before they get to this geometric convergence regime. In our case, there's no such finite time. And there's no restriction on the noise. So this is a few remarks here that I believe are important. Let me say spend 2 minutes on motivating why we really did drop the DI, and some things about the proof. I'm going to say proof sketch. That's. I don't think I will be able to sketch the full proof, but let me just say a few things. D equals 1. Let's look at one layer. No compressed sensing. Phi is identity. No noise. Okay. In that case, the problem becomes you have Y is equal to sigma of W1 Z star, and you want to find Z star. Okay. And in this particular case, here's a claim that I will. If you take our plugin iterates and take the first iterate and take its expected value, you get Z star. So the first iteration of plugin is an unbiased estimator.
So, Ozgur, what's the expectation over?
The expectation is over, Brian, this matrix here.
Got it.
Okay, W1 is a Gaussian matrix. Okay. All right. So where does this come from? There is a lemma. This is due to I know it. We know it. I mean, Yaniv and Roman version has a paper where their results imply this lemma directly, but there's also earlier observations of this, I believe, by Brillinger and potentially maybe others. And here's the lemma. It says that take a sigma function from R to R, and it is positively homogeneous. Take a matrix A, M by N, with IID with Gaussian entries, appropriately normalized, then the expected value of A transpose sigma AX is lambda times X. And here lambda has an explicit value. It's the expectation of G times sigma of G, where G is a standard normal. Okay? And in particular, if you pick sigma to be ReLU, then lambda is a half. Okay? And this is why I picked the step size as 2 to the D. I mean, it's going to be very apparent when I write it. Let me just now prove the claim that I've made about this is the lemma, and the proof of the claim becomes trivial because what do you have? You have Z1 is equal to Z0. Sorry, let me just, maybe I said proof of the claim. So Z1 is Z0. Where's my algorithm? My algorithm is right here. Okay, Z1 is Z0. It's right here. Minus 2, D is 1. W1 transpose sigma, phi is identity. Okay, G is sigma of its argument. The W1 times its argument. So W1 times Z0. Okay, minus Y, which is sigma of W1 times Z star. Okay, so this is Z1. Now, if you take the expected value of this and expected value wherever here, you immediately observe that what you get is expected value of Z1 is Z0 minus 2 times half Z0 plus 2 times half Z star, which is Z star. Okay. So again, this is just the motivation, but it kind of tells us that when we have value, we can kind of get rid of this value from the picture, and then in expectation things might work fine, and then you can move from there. And it turns out that is indeed the case. Of course, it's not easy. Further iterations are not unbiased estimators. So then you have to use heavier machinery here, and the proof is based on generic chaining of mixed tail processes. And also some counting of subspaces when you want to go to a D-layer network. Okay, to go to D-layers, need to count subspaces basically that such that the range of G can be covered. That cover range of G. Okay, so let me stop here. This is, as I said, I mean it's technical, and it's I don't think it's I have 4 minutes left. Let me just very quickly say some extensions and improvements. Improvements. These are kind of cool because the setting, we make quite a few assumptions here, right? And we want to relax them a little bit. The first one is the big assumption where we replace the prior with basically being in the range of the generator. And one thing you can do is you can say, well, maybe I'm going to call this projected plugin. Given the time, let me quickly try to motivate what I'm saying. Remember, this was not an arbitrary vector. It was a Gaussian vector. And therefore, my X, my signal class, should be not necessarily the range of G, but the range of vectors that are likely coming from this draw of Z. And we know that, for example, the Z, if you look at the 2 norm of Z, that should be, roughly speaking, square root of N naught, right? So we should be able to incorporate this information somehow. So we thought maybe we modify plugin, and we modify plugin in the following way. And something similar can be done to gradient descent, at least algorithmically. If in the case of plugin, we can also prove that this works. So assume that your signal, the latent code of the signal, comes from a ball of radius, let's say R tilde. R tilde is probably not exactly equal to this. That would be too restrictive, but a little bit bigger than that. And then this is a convex set. Project everything onto this convex set. And in other words, when you run plugin, when you do this, that k+1, and then you get that k minus the whole expressions here. So you just take this whole thing and put a projection in front of it. So project onto B. And if you do this, it turns out that first of all, you can prove that this also converges and with the same error bounds. I don't know if we can't improve the error bounds, but we can keep them as they are. And in experiments, this performed way better than either gradient descent or plugin. Okay, so this is one. The second one is we can handle bias now. As long as the bias is also a Gaussian vector, the variance is okay. The normalization is not a problem, but it has to be a Gaussian vector. If it is, we can handle it. We can move from Gaussian weight matrices to symmetric isotropic sub-Gaussian. Matrices. And in compressed sensing side, we can work with sub-Gaussian compressed sensing matrices. In compressed sensing matrices. And we can incorporate quantization into the reconstruction. And this is just one example. There are other things that potentially one could incorporate as well. But this is one thing that improves the reconstruction when you know that you have quantized your measurements. Okay, so given the time, I think my time is up now. I'm happy to stop here. I was hoping to show some experimental results. If there is any flexibility, I can connect the PowerPoint and show a few pictures, but I'm also happy to stop here. So Ryan, tell me what you prefer.
Maybe how about we do this? If you can, while trying to set up the PowerPoint, we can take a few questions. That way we can optimize time.
Absolutely.
Great. So I'll start with a question we got from the Q&A. And in particular, Wolfgang is wondering if the weight matrices of the network are Gaussian random, then the network isn't really encoding specific knowledge about the problem, but it's a structural prior. So how should we think geometrically of this prior? So what kind of prior would a random network like this correspond to?
That's a good question. First of all, I don't know the answer, what kind of prior it would correspond to. What I can say is that we think of this as a way to go towards a more practical scenario where I would take the weights of a trained network and which then the prior would correspond to whatever the signal model is with which it was trained. And then establish criteria to evaluate whether this algorithm or any of algorithms in this family would be able to invert this given network. We are far from there, but we have some kind of an understanding that, for example, symmetry of the weight matrices is crucial. We have, when I show the experiments, I'll show that they kind of work on trained networks. For example, we have an MNIST experiment where we can invert a real trained generative model, which has bias. In fact, that network even has a sigmoid in its last layer. So again, the reason why we are looking at random networks is not necessarily because we think they are in their as they are really that important per se, but they are providing a gateway to understanding what makes these algorithms work. That said, I also know that some of these over-parameterized models, when you train them with an initial weight distribution of Gaussian, then they don't move too much, and their weights actually are kind of like Gaussian. I don't know what kind of implication that would have because they're still not Gaussian. But again, I want to emphasize that we want to understand settings, situations, conditions under which we could understand whether a given generative network that is trained can be inverted. That's the direction we want to go.
Great. I actually have a question related, rather related to the case when your generative model, it doesn't exactly capture your signal, but rather the signal is equal to generative model plus something, and potentially that something may not be independent of the model, right? Because the model captures some properties, but misses some properties, potentially also structurally. So do you have any thoughts about the importance of the independence assumption on the noise?
The independence assumption on the noise, you're right. You're right. For example, quantization is kind of like that, right? You have
similarly compressive versus sparse models.
Compressive versus sparse models, yes. That's a great question, Ryan. I thought about the following question, which I also have no answer for. If you wanted to further regularize in the signal space, which is also basically saying that, okay, I have a generative model, but maybe it's a little bit too big. So I want to constrain still further, impose maybe sparsity on with respect to something or something else. How would I regularize? And that is, it's easy to regularize in the latent code space. It's not that easy to regularize in the signal space. About what you say, I think I have no immediate answer.
Do you expect, for example, like in the bound, to have something like you would in compressed sensing, where there's a term related to the deviation from the model?
Could be. And the deviation from the model is, there are two deviations, right? One is the range of the generator, which all these algorithms assume.
Right.
The other one is the within the range, the deviation from the prior.
Right.
And I think those two are two different issues that need to be addressed differently. And the projection idea that we have kind of was to address this deviation from the prior issue, because if you take a signal and you multiply the signal by a positive constant, then your function is positively homogeneous, so it's not going to change anything. But as soon as you add noise to it, then you are moving in the signal space, and that in return, when you invert, has a non-homogeneous impact, and it is probably taking you away from the right place. So yeah, I mean, these are great questions, and we are thinking about some of them, but there's way more to think about. I guess my answer.
Yeah. One question from Sina Shahsavari is about the constant CD in plugin and how it depends on the linear polynomial in the sampling complexity.
In the sampling complexity, let me the one here you're talking about the compressed sensing one, right?
Yes. So
let me find where did I say the CD? I'm just trying to find that. Okay, in assumption something. Assumption 8.3. Yeah. So actually it's not too bad. There's an exponential dependence on D, but in terms of other dimensions, things actually were reasonably constant like. So if and it's exponential, but it's not badly exponential. I'm trying to see the paper. Honestly, I don't exactly remember. Yeah, so it's something like a constant times 4 to the d. And given that, I mean, of course, if you have a network with depth 100, then it's not good. But but in any reasonable depth, it's not a big constant. Given that n naught is really small.
Sounds good.
Yeah.
Okay, so I think those are the questions in the Q&A. I think we could spend a couple of minutes on the numerics if you like.
So I will ask you a favor if I email you the PowerPoint, because now I'm on my iPad. I realize that I don't have a immediate way of doing this. Can you?
I don't think I have PowerPoint, so I can't guarantee you.
Okay. Okay.
I can do it if you want.
Oh, Soledad can do it.
Okay. So the other option is I connect to Zoom from my computer too, and I think that should work. You know what? That might be a better way to do this. So this is a staple. So that I will email it to you if this doesn't work. I'm just going to very quickly try this. If you let me share from the second place that I went to. Now I see my talk, so it looks good. I'm going
recording in progress.
I will mute this.
You should be clear to share.
Yeah, this seems to be some.
Maybe disconnect the iPad.
Oh yeah. I hope you can hear me now.
Yes.
Yes.
Okay.
No feedback even.
It's been adventures today. All right. I'm going to, can I share? Yeah, I think I can share. Let me share my screen, and this is the PowerPoint. Let me know if you can see it.
Yep.
Good.
Okay. So here's some very quick experiments. This is denoising, and you can see on the left the latent code recovery, and on the right the signal recovery. And the color codes are, it has plugin and gradient descent, and projected plugin and projected gradient descent. And here, as you can see, plugin is doing a little bit worse than the other three. By projecting, we are getting it to roughly the same level as the gradient descent and projected gradient descent. But remember that it's much simpler to implement. Now, and the number of, here the latent code dimension is 20, and we have the signal dimension is 750. If we go to less redundancy, this is the latent code dimension is 70, and the signal dimension is 750. You can see that the projected algorithms perform way better in the moderate to higher noise levels. So this is what I was trying to say. When you deviate from the model by noise and other imperfections, then it seems that this projection, which is imposing the prior stronger, is helping. Early stopping helps, by the way. That is just to illustrate that. And let me show you, this is a compressed sensing experiment. These are all, by the way, these are synthetic experiments. And you can see, again, the various algorithms, they work perfectly when there's no noise. And then there's the four algorithms. they are doing reasonably well, especially in the signal space. If you look at the signal space, this is not what I said. I said that the error bound on the latent code was smaller. The other one was 3 times, but at the end, what you get is a much better reconstruction in the signal space compared to the latent code space, which tells me there is some redundancy here, and that is helping us in the recovery in the signal space. This is a better example for that. As you can see, the relative error in the latent code space, this is a smaller sampling rate, or redundant. The latent code space is 70-dimensional here. The relative error in the code aspect is much bigger, and the relative error in the reconstruction is much smaller. Whereas it's at the level of, if we got relative error in the signal space that was like the latent code space, that would be a meaningless result, because anything bigger than 1 is really not meaningful. But here we are getting very good reconstruction, whereas in the corresponding latent code recovery is terrible. So this is, again, by increasing the latent code dimension, we got to a redundant setting. And this also, I think, answers one of the earlier questions. So how to choose that K? K is here the latent code dimension and not. And as you can see, by picking it bigger, we are getting a more redundant representation, which gives us better reconstruction, even though not a unique. It kind of is like the sparse approximation setting. And finally, let me show you on real network. So this is an MNIST trained network. Again, all the 4 algorithms, and again in the signal space, they do a pretty good job. These are relative errors on the order of 0.05 to 0.2, and the dimensions of this is relatively the same. We have 300 measurements, and the signal space is 784, and the latent code is 20-dimensional. And here's an experiment where we had an original image, and then we added basically noise to it with a noise level of 0.5. And these are the reconstructions we get. And as you can see, they're all good. And this is plug-in, projected plug-in, gradient descent, and projected gradient descent. So the algorithms work fine on this trained network. Very quickly, this is 1-bit quantization. It gives you essentially what you would expect to get with plug-in reconstruction. This is not, you can't do this really with gradient descent. And here is what I meant when I said you can incorporate quantization into the reconstruction. So what we are doing is, here, this is a multi-bit quantization scenario with high resolution quantization. And we are incorporating the quantizer into plugin. Inside that iteration, every time, instead of trying to match the measurements, we are trying to find something whose quantized value matches the measurements which are quantized. And when you do that, you see here the blue is plugin, regular plugin, red is gradient descent, which treats basically quantized measurements as measurements, and so quantization error is embedded inside or absorbed into the noise. And the black is the plug-in with modification with respect to the quantizer, and there's orders of magnitude improvement here. And with that, I'll stop. This is all I have in terms of numerical experiments today. I might have more in a few weeks.
Thank you, Ozgur. We'll just close with one last very simple question, whether the step size is 2 to the D as in the theory, or whether here you're just picking something that works in practice.
That's a fantastic question. This is, in these experiments, we do choose 2 to the D, but to be basically loyal to the theory, it seems that a little bit smaller might be better, especially in high noise regimes. Something on the order of √2 to the D seems to be in these experiments performing the best. The proofs we have apply to smaller step sizes, but they don't improve based on smaller step size. Basically, the upper bounds remain the same. They're valid for a step size up to some number. And the reason why we 2 to the D makes things much easier when you're easier to write, and it connects with our motivation. So we kept everything 2 to the D.
Fantastic. Well, thank you so much, Ozgur, for a great talk, and thank you all for being here.
Thank